Welcome back. In this video, we will discuss the second Python script entitled calculate_fips.py. To do this, we will first download the set of data associated with the Prisms-Fatigue manuscript. First, navigate to the Prisms Center on GitHub. You can simply Google Prisms Center GitHub, and this should be the first link. Next, click on Fatigue. This page is still under development, but in the description, in the README section here, there will be a link to Materials Commons. So in this case, it is this doi.org link here. And if we click on this, this will take us to the Materials Common page, and this contains the data that we will post-process. You will notice that this data is quite large in size, over 30 gigabytes, because this contains not only the instantiation data for the microstructures, but also the results from the crystal plasticity finite element method simulations. A very quick and efficient way to download all these files is using Globus. If users click on this Using Globus link, this should open up a second page. And in this page, on the left-hand side, it lists the 4 folders that are part of this dataset. And on the right-hand side, you can navigate to your own desktop directory. So users will need to create a user account on Globus, but this is fairly easy to do, and it appears to allow you to make a user account using something like org ID or a Google account. Let's first take a look at this data before we examine the calculate_fips.py script. So this folder here contains the source scripts that has the Dream 3D files we discussed and the 5 Python scripts. And in this tutorial folder here, this is where users should place their files downloaded from Material Commons. Let's investigate the contents of one of these folders, Free Surface Effects. So the first 3 folders indicate the texture of the instantiations that were generated. So we have cubic, random, and rolled, and these all have the equiax grain morphology, and they were simulated with one set of faces set to free surfaces. So for instance, in the cubic equiax free surface, we have a total of 301 files. So this has the instantiation data for 30 microstructures that are cubic in crystallographic texture with equiax grain morphology, and with one set of parallel faces set to non-periodic as we described in the previous video. This also includes these maxcomp and max10 CSV files, and these files have the results from the crystal plasticity finite element method simulations. So compared to the previous instantiations we created in the last video, the only additions to this folder are these results files. The same is true for the random and rolled folders. They still have 301 files with microstructure data and additionally a maxcomp and max10 CSV file for each microstructure. This last folder, entitled Simulation Files, contains the files that are necessary to simulate these microstructures in Prisms-plasticity. So let's discuss each one of these. The first file, entitled Latent Hardening Ratio, simply lists the latent hardening ratios for each of the 12 slip systems of this face-centered cubic material. Slip Directions and Slip Normals lists the slip system directions and the vector normal to the slip plane for each of the 12 slip systems. Periodic BC Constraints is a special file that indicates constraints so we can emulate bulk subsurface response, in this case in the X and Z direction, but still allowing for a free surface in the Y direction. So this is very important because for these set of simulations in the free surface effect folder, we want to simulate these with the Y surface as a free surface. Whereas in the other simulations that we'll talk about in just a minute, those will be periodic in all 3 directions. And users will notice that this particular periodic BC constraints file has 78 lines, whereas the other periodic BC's constraints text file for fully periodic simulations will be slightly longer to impose those additional constraints. The final file in this folder is the PRM file that specifies the parameters for the simulation and microstructure. So here we specify the size and the shape of the microstructures as well as other settings. Here we specify what types of boundary conditions we want to impose. And these other values here indicate the type of loading that we will apply. These values then list some properties of the elastic stiffness matrix and crystal plasticity flow rule. Finally, on the bottom, we specify what grain ID and orientations file we would like to include with this simulation. So if we go back up to this folder for free surface effects and go to one of the folders, for instance, the cubic equiaxed free surface. So we have 30 microstructures here. So to simulate these, we would essentially point to each one of these pairs of grain ID and orientation.txt files. In the simulation files folder, we have a source folder with 3 C++ codes. So these are specific modifications to the Prisms-plasticity code that will export specifically the variables that we need to recreate the data in the Prisms-Fatigue manuscript. So specifically, update after increment.cc that is listed here is specific for Prisms-Fatigue in that it will output for every quadrature point the slip value at every slip system and the stress normal to those slip systems. Additionally, it will include some values of the plastic strain tensor that we need for the gamma plane. What users need to do is copy and paste these C++ files to the Prisms-plasticity folder and then recompile Prisms-plasticity. To quickly demonstrate this, let me navigate to the Prisms-plasticity GitHub page. So this is the Prisms Center page. I will click on Plasticity, then click on Source, Material Models, and Crystal Plasticity. So here we also have an instance of crystalplasticity.cc, userfunctions.cc, and update after increment.cc. These are the defaults in Prisms-plasticity, but as I mentioned, these ones will give us the results that we need to calculate exactly the same FIPs as in the Prisms-Fatigue manuscript. Let's summarize this very quickly. So in each one of these 3 folders, we have 30 instantiations. And to simulate each one of these are the files that we need. And the only file that we will change for every instantiation is the .prm, where we specify a different grain ID and orientations text file. I showed that we have 3 .cc files in a source folder from the Materials Commons download, but they are no longer there. Instead, users can get these 3 files by navigating to the Prisms Center Fatigue page, clicking on Source, and clicking on Material Models. So this has the 3 .cc files. And the reason users should grab these from the website and disregard the ones that were uploaded on Materials Commons is because these ones will be periodically updated by us. Let's take a look at the other folders we have. The multiaxial fatigue folder will not be discussed until we get to the last video on the gamma plane. Let's examine the grain morphology effects folder. This folder has the same structure, but now we have cubic elongated, random elongated, and rolled elongated files. These still contain simply the instantiations and results files for the other application that is described in the Prisms-Fatigue manuscript. This one only has 271 items as opposed to 301, because when we were looking at the free surface microstructures, for each one we have the text file entitled split grains to indicate which grains are split by the free surface. In the grain morphology and texture effects applications, all the simulations and microstructures are fully periodic, so we expect to have 30 less files. The simulation files are identical, as well as the source files for Prisms-plasticity, except for this periodic boundary conditions constraint text file. So because this is for fully periodic boundary conditions, if we examine the length of this, we see that it is now 110 lines in length as opposed to 78 lines in length like the free surface effects.prm file. Let's summarize the three folders. Free surface contains the instantiations and simulation results of the three textures with equiax grain morphology and one set of surfaces set to traction-free free surfaces. So these emulate the response of a thin sheet or a thin film material. Grain morphology effects contains those same three crystallographic textures, but with fully periodic boundary conditions and elongated grain morphology. And finally, texture effect contains the same three crystallographic textures, fully periodic boundary conditions, and equiax grain morphology. Before we examine the calculate FIPs.py script, let's investigate what is in each one of these maxcomp and max10 CSV files. The slide here describes the simulations that take place in Prisms-Fatigue, in particular for the Prisms-Fatigue manuscript. Each microstructure undergoes fully reversed straining to a strain amplitude of 0.7%. We start by compressing the material and then pulling it in tension and then going back to zero strain. The stress strain curve here is for one of the random textured aluminum 7075 microstructures. In the manuscript, we apply 3 cycles in total, so the stress strain curve here shows the result of the macroscopic stress strain curve. We calculate FIPs across the last loading cycle, and in particular, we calculate this Fatemi-Sosi FIP. In this case, this is a crystallographic or transgranular version of the Fatemi-Sosi FIP. So we calculate this FIP for every slip system at every element in the microstructure. Each maxcomp and max10 CSV file is associated with the quadrature output at the final point of max compression and max tension in the simulation. To calculate this FIP, we need this variable, which is the plastic shear strain range for each slip system and the stress normal to that slip plane. Let's open one of these files. So this is one of the results files, and we will go through what each of these columns means. The first column is simply the grain ID. The next 3 columns indicate the X, Y, and Z positions of the quadrature point in question. The following 12 columns indicate the current value of the plastic shear strain on each of the 12 slip systems. The other 12 columns indicate the stress normal to each of these slip planes. So in this case, we would expect that this value is the same across these 3 columns, because although this indicates the stress normal to slip systems 1, 2, and 3, they occur on the same slip plane. The max10 CSV file contains the same information. The reason we need both max10 and maxcomp for the FIP that we want to calculate is because we want to calculate the range of plastic shear strain. so we will end up subtracting the values of plastic shear strain between the max 10 and max compression points in the simulation. Let's take a look at the calculate FIPs.py script, and we'll start with the main function. The first variable that users will change is the directory variable, which simply points to where the microstructure files and simulation results are kept. In this case, it's pointing to the free surface effect folder and the cubic equiax free surface folder. The next variable dictates the number of voxels in each of the X, Y, and Z directions. So here it's listed as 29 by 29 by 29. Num instantiations once again specifies the number of microstructures in this folder. So in this case, we have 30 microstructures. FIP type specifies the FIP that should be calculated, and I will show in just a second how this changes how the FIP is calculated in the function called import prisms data. KFIP and sigma y are parameters that we need to calculate the Fatemi-Sosi FIP, and these were indicated in the equation shown here as K and sigma y. Number of slip systems simply specifies the number of slip systems in this material system. Because for the Fatemi-Sosi FIP, because we calculate a FIP for every slip system, this is how many FIPs we will get for every element. For the time, we can set gamma plane simulation to false. This is because the way that the gamma plane simulations are structured will call the import prisms data function a little bit differently. So we will go over this in the final video where we describe the gamma plane. Visualize VTK FIPs. We will set this to true. And what this will allow us to do is visualize the FIPs by appending them to the VTK file. And this last variable, num gamma plane folders, can also be set to 1 or honestly anything, because this is only used if gamma plane simulations is set to true. So the rest of this function will call the import prisms data and append FIPs to VTK functions to evaluate the FIPs. Let's walk through what goes on in this function. The first part of the code simply reads in the max comp and max 10 CSV files for each instantiation. So this function is called once for every set of these CSV files. These next lines of code simply read the information using the pandas module. Now, this bit of code here is commented out. This is because Prisms can employ full integration elements, which would give 8 quadrature outputs for each element. But in this case, for Prisms-Fatigue, the Prisms-plasticity simulations used reduced integration elements. So that means we only have 1 quadrature output point for every element. If we ran full integration elements, then we would simply uncomment these lines of code, and this would average the values of the 8 quadrature points for each element. This is because we will calculate 1 FIP for every element for every slip system. So we need to average these values. This section organizes the rows by X, Y, and Z in ascending order, so it matches how the elements are listed in the pickle files by generate microstructures.py. Now, the remainder of this function is very specific to the Fatemi-Sosi FIP. So this is what users will change the most when they define a new FIP. In the case of this FIP, we first calculate the plastic shear strain range, which is this variable delta gamma. So this is the difference in the values between maximum tension and max compression. And we then define slip values as the columns 4 through 16. So then slip values is the plastic shear strain range for our 12 slip systems. As I indicated previously, the next 12 columns have the normal stress to each of the slip planes. In the manuscript, users will read that for any normal stress that is below 0, we simply set those values to 0 in the calculation of the Fatemi-Sosi FIP. This last part of the code actually calculates the Fatemi-Sosi FIP. But we also included a FIP that only considers the plastic shear strain range. If the user were to input an undefined FIP as FIP type in the main function, this would raise an error. But later on, I will go through exactly what it takes to add a new FIP type here. So after the FIP is calculated, it is stored in the same type of pickle format in this section here. Once again, I will talk about this gamma plane simulations variable and what this means for the calculate fips.py script in the final video. The other function in this script is pretty straightforward. Basically, this function will read in the pickle file that we just saved with our FIPs. It will look for the VTK file that we generated in the previous script. It will make a new VTK file and append the FIPs we calculated so we can visualize them. Now, what's important to note is that in the Fatemi-Sosi FIP we described, there are 12 values for every element. So in this case, what the code does is it first finds the maximum FIP per element out of the 12 and appends that one to the VTK file. So let's execute this script on the files that we downloaded from Materials Commons. So I will minimize these here and I will open up a command prompt and move this here. And then I will navigate to the folder, the source directory, so I understand things look a little bit different than in the generate microstructures.py. Because in that video we just wanted to generate microstructures, but in this one we will actually use the exact same files that we used in the Prisms-Fatigue manuscript. So I will navigate to this source directory, and we will first execute this for free surface effects, cubic equiaxed free surface, and this is already defined in the calculate fips.py script as the directory. We have the correct number of voxels for each microstructure, and we have 30 microstructures in this case. We'll calculate the Fatemi-Sosi FIP, and everything else should be set as we have indicated here. So in the command prompt, I will execute python calculate fips.py, and we should see some new files appearing in this folder here. So it is all done. Let's look in this folder. I'm going to sort by date modified. So now we have these extra files here. We have prisms, fs, FIP, and we have 30 of these, one for every microstructure, and we have the appended VTK file. So let's look at this VTK file first. So this will look very similar to what we saw in the previous video. We first hit apply, then we can look at our options, and now we have a new visualization option, max element FIP. And if we visualize this, what this will show us now is the maximum FIP per element for the microstructure. So this is neat because we can then go on threshold, and if we make sure to change this to max element FIP down here by scalars and back up here, so now we could visualize where the maximum FIPs are by elements. So let's scroll a little bit higher here, and we can really single out where we have the highest elemental FIPs. So this can be very useful to investigate what's going on in our simulations. So this is just one of the possibilities because users can really modify these scripts to do a whole lot of different visualizations. Let's take a look at this other file that was generated. So I am going to open it up in the interactive Python mode. So I will navigate to this directory with all these files, and I will type IPython for interactive mode. We will import pickle, the pickle module as P, and we will define fname as one of the files for these FIPs. So fname is equal to prisms fs fip underscore 0. The next line will be h1 is equal to open fname comma rb. Fname and h1 are completely arbitrary. You could name those whatever you want. But then let's say fips is equal to p.load or pickle.load if you just imported pickle without including this as p. p.load h1, and then we will do h1.close just to close that file. And now let's import numpy as well as np, and we'll look at what we just imported. So numpy.shape of fips shows that we have an array that's 24,389 by 12. So this is actually the number of elements we have, and this is the number of slip systems we have. So we just basically imported the FIPs, and in this interactive mode we could do more investigations. So FIPs of 0 will give me the FIPs of element number 0 for the 12 slip systems. So I'm just really quickly demonstrating how versatile this pickle format is here in terms of calculating FIPs and being able to further investigate them. So let's go through the process of defining a new FIP from scratch. Say we wanted to consider only the maximum normal stress in our simulations. So in this case, we would do something like changing FIP type to normal underscore stress. If we need to define another variable to calculate this FIP, we could simply add a new variable under this list here. For instance, let's do variable underscore stress underscore normal and set this to 15. Just for the sake of argument that we need this to calculate the FIP. And then we could actually just include this in this array, in this list of FIPs param, because FIP type and FIPs param are both going to get sent to the import prisms data function. So now we can go up to that function, and down here where it says calculate FIPs, we could include a new line. So let's say if else FIP type is equal to normal stress, then we could say that for every slip system, so that will not change, we'll say that the FIPs stored, that's going to be equal to the NP max of, I suppose it would be the normal stress here that we have. So this is the final result that we would put, and this would basically make an array where we have for every element and slip system, this FIP is just the normal stress, and this will be pulled from the point of max tension. More specifically, these values of normal stress would be extracted from the CSV file max10 that comes from the point of maximum tension in the simulation. So the values that we use to calculate this FIP are the ones that are by default included in the files that are exported. So these files here that are the max comp and max 10, as we saw, these columns are for the plastic shear strain and for the stress normal to the slip plane. But what if we want to calculate a FIP that needs a state variable that is not defined here? Well, in that case, users will need to edit the update after increment.cc file. So let's take a look at that. And this is available in simulation files as I described previously, as well as on the GitHub fatigue folder in the source folder. So update after increment, we could open that in Notepad++ or in the text editor of your choice. And if we scroll down here, we will reach the part of the code where we have the outputs for every quadrature point. So here we see that we export first the grain ID, then the X, Y, and Z positions, then for every slip system, the plastic shear strain, and the stress normal to that. These values are for the gamma plane, so we won't discuss that. But basically, this is where we're going to put the new outputs that we need if we have some new complex FIP. And these files are, of course, associated with calculateplasticity.cc. So in this file, this is where we define the constitutive model. So if users need to import a new model or define new state variables, this is where it will be done. And then the update after increment, this is what will be updated to add new columns with information for new FIP calculations. The other thing users need to take into account is that we simply state what column will contain what information. So right now we're saying that certain values are in certain columns here. If we go back on the script, we see that we pull values from certain columns that correspond to certain things. So the slip values correspond to columns 4 through 16, and the normal stress corresponds to columns 16 through 28. So users need to be really careful if they edit this to make sure that the values they pull in this script corresponds to the correct values that are written to the .csv file. As I mentioned, these .cc files were initially included in the source folder as part of the download from Materials Commons, but they are no longer there. They are now exclusively in the Material Models folder in the source folder on the Prisms-Fatigue GitHub page. So users will modify the CC files in here and then place these into the source Material Models Crystal Plasticity folder in Prisms-plasticity and then recompile the package. And this will give the correct column outputs for the quadrature outputs. So now we can calculate FIPs for the remainder of the folders. We can quit this interactive mode of Python and navigate back to the source directory that has the calculatefips.py script. And in the calculatefips.py script, I will simply change the FIP type back to Fatemi-Sosi FIP. And I should mention that based on what you name the FIP, so FIP type, that will dictate the pickle file that is created. So the one we already made, we have this file, prisms, and then fs_FIP. So if we ran the FIP that was called normal_stress, then we would have prisms_normal_stress_0.p. So that's very useful because we could create as many pickle files with different FIPs as we want. The last part of this tutorial then requires the user to execute this script on the remaining 9 folders. So I just saved this. The path is now free surface and then random equiax free surface. So we have 301 items or files in this folder. So I will execute the calculatefips.py script once more. And now this should populate and we should get 60 more files, 30 of the appended VTK and 30 new FIP files. So now we're done running, and if we look at the new files, there are in fact 30 new VTK files and 30 new pickle files. For the sake of demonstration, I will execute the script using an absolute definition of the directory path. So I will comment out this first instance of directory, uncomment out this line, and replace this path here. And now we will calculate FIPs for this last folder. And this is just demonstrating that regardless of how you define the path, it's going to work in either way. But this convention gets a little more risky if you're moving files around on your computer. Let's summarize what was discussed in this video. We first downloaded all the simulation data from the Prisms-Fatigue manuscript from Materials Commons and went through each folder and file. We then talked in depth through the calculate FIPs.py script and investigated the .csv simulation results files from Prisms-plasticity. We calculated FIPs for several folders that we downloaded. In the next video, we will perform volume averaging for these FIPs over various domains. Thank you for your attention, and I'll see you next time.